Okay, so for this section, I'm not going to be teaching you much. I'm mainly just going to be giving you two tricky questions. A little bit trickier than you've been looking at before, so I reckon you should have enough time to give them a decent attempt. But I do have this tradition of a try now question at the beginning, so let's have a look at this. This is not necessarily something that is part of the exam spec. I just want to make that clear. It would be, I think, part of the second further maths textbook, but it is a very interesting idea, I think, and it's, I think, something that underlines a lot of the understanding of how springs and strings work. So I think it's worth asking it and worth understanding. So if you had physics, you'll have an advantage for this, but if you're not studying physics, perhaps less so. Again, classically, object on a spring, I let go of it, it bounces up and down, right? So imagine you've got this object just sort of bouncing up and down. In the real world, eventually it'll settle down because of friction and air resistance and all sorts of things which are effectively doing work against the motion. But at least initially, you can imagine an object just sort of bouncing, oscillating up and down, right? And what's shown in this graph is 3 attempts at modeling this motion. And as I've said in the text itself, the object drops 1 meter, then it comes back up again, back to where it started. It'll still keep moving, it'll then have to go up and then back down, but let's just focus on a snapshot of the motion. So the snapshot is at 0 displacement, it then, one of these lines, whichever one it is increasing its displacement, and then it decreases in displacement and comes back to where it started, and that whole thing took 1 second. So what I've done is I've picked 3 possible equations and I've forced them to all have a duration of 1 second and have a maximum displacement of 1 second. Okay, one of these is an accurate model in terms of the real physics of the universe, right? How does physics actually work in this particular universe? It's one of these equations for this scenario. So the other 2 are just wrong. The question then is, which one do you think it is? Which one to you seems intuitive? Is it, and you don't have to worry about the exact form, but is it a transformation in this first case of a sine graph? Is it a transformation of a modulus graph with the sharp sort of turn? Is it a transformation of a polynomial, right? So in this case, x squared. Which of those 3 do you think it is? You can pause now if you want to think, or if you want to try and experiment with some ideas. You could potentially derive it yourself. The answer, I will tell you, is in fact this one. Okay, it's a sine graph, right? So once again, trigonometry reveals itself to being fundamental in how the universe operates. It's the black, is it black? No, it's the red one. It turns out the x squared and the sine graph are extremely close, right? Partly to do with small approximation. If you remember, you can approximate a sine graph quite accurately with a second order polynomial, but it is the red graph. Okay, so it follows a sine wave. So you can think of this oscillating object. Let me do it with my laser pointer. You know, as this object on a spring oscillates up and down, over time, it traces out a sine graph, right? So equivalently, that would be kind of like imagining that I move the dot to the right at constant speed as it oscillates, and you're drawing out a sine graph. Okay, and that's effectively what the motion of a spring is. Okay, obviously I've drawn it quite poorly there, but you get the idea. I'll just drop the name for it actually, no point withholding it from you. It's not part of this chapter, possibly not in the textbook, but you're in it also to just understand how things work as well, I hope. So it's good to know what the wording is. This is just called simple harmonic motion. There are many things which exhibit simple harmonic motion, but springs and elastic strings are one of those. So it's not unique to springs, but it is one example of it. Okay, often just shortened to SHM. Okay, so simple harmonic motion follows a sine or cos graph when you plot its displacement against time. Cool. All right, so let's take a look at these two questions that I've been promising you, the tricky ones. We'll take a look at the first. Okay, so here's the first of the two. I want to kind of give you the option of attempting this in stages, or maybe not stages, but in difficulty levels. So hardest difficulty is you're going to pause the video in a moment and you're not going to get any information from me. Okay, so that's your first choice. Your second choice is I will, at a minimum, draw the diagram of what's going on. And in fact, those are your two choices. The third choice ultimately is cheating and looking at the answer, which means you haven't really learned anything, which you're not going to do. So if you want to just read the question, attempt it yourself, and see if you can prove it, then please go ahead. You can pause the video now. Okay, and if you have already tried that and you struggled, or you want a little bit of help first, then you can continue listening. If you've already tried, just skip quickly. So I think part of the difficulty from the question might even just be visualizing the scenario and understanding what it's trying to, what you're trying to actually show, because it seems a bit counterintuitive. So the idea is you've got this table, right, and there's a hole in the table, right? So I'm doing it side on. Okay, here's your table, and there's this little hole there that I've left as a gap. You've got an object A here, and you've got an object, I've got the right way around, B here, and this elastic string is connecting the two of them like this. Okay, it's drawn you know, a little bit abstractly. Obviously the string would go directly into the hole. You're imagining A and B are models as particles, as it says here. And the weird scenario which they want you to prove is that, okay, first of all, if the green string was just a normal string, obviously B is going to fall down and A is going to move to the right. However, what they're asking you to prove here is that given the information, the fact that the green string is elastic, the fact that this distance here is 2.5, this distance here is 2, and the modulus of elasticity is 8, etc., the natural length and so on. Given all that, show that in fact in this case A is going to move to the right, but B is going to move up, right? And that can only happen because the string is elastic. So it seems a bit counterintuitive. You'd think obviously B is going to fall down, but in this case apparently not. Can you prove it? Okay, so that's my little hint there to just make it clear. Yes, in fact you are trying to show A moves right, B moves up. Can you do it? Pause the video now, give it a go if you haven't already. Okay, let's look at the full solution. Okay, so there you've got the full working. It turns out, given that extension, it turns out the tension in the elastic string is 64. And then you just have to consider, are the competing forces for each particle less than or equal to 64? In both cases, for A, the friction was less than 64. And for B, the weight caused by gravity was also less than 64. Therefore, resultant forces in both cases are towards the hole. I'll just leave, just pause it if you need to, if you want to have a look at that working. Okay, and here it gets interesting, I think, and a bit more tricky. I'll do the same thing again. I'll give you the option of continuing to listen. If you want me to just draw out the diagram, you can check that you've done it the same correctly. If you don't want a hint and you want the satisfaction of having done it entirely yourself and having that particular skill to be able to do it yourself, please go ahead. You can pause the video now. Okay, and if you want the help, here's the situation we're drawing. We've got our 2 points A and B. They are 4A apart. You've got an elastic spring, let's do it in green, string, sorry. It's taut, just taut when its ends are fixed at A and B, so its natural length is 4A. And at 3A, we've attached an object and it's going to be at a 90-degree angle when the particle rests in equilibrium. So if I try and just draw that as accurately as I can, that'll have to do. That is 90 degrees. And this is of length A, and this is of length 3A. And this is our point P here. Okay, where the object is. In terms of the diagram, I think it's worth dropping a perpendicular here so that it makes it possible to resolve things horizontally and vertically if you so need to. Notice that it says a heavy particle is attached to the string, but it doesn't give its mass. And then we're going to show a result which doesn't involve mass. So what that implies is that the mass itself is irrelevant. However, we still need to include it because it exists. So it's a non-zero mass, right? So at the very least, you're going to want to draw a force of mg from that particle there, okay? So the mass was probably going to cancel at some point in your calculations, but it needs to be there. It's not zero. Okay. Finally, the thing that's missing itself is the angle. The angle is BAP, so it's this one, right? So that's the angle. Okay. So what we've effectively got is, it's almost a bit of a geometry question combined with a few other things. You've got a right angle triangle, right? You know the side lengths. In which case, sorry, I should clarify on the side lengths. They're not 3A and A, sorry, I should add to that. That would be before they were stretched, right? So this is the key part of the hint, I think. Let's give them each an extension, let's say X and Y, right? Because they've both been stretched. So one of the side lengths is 3A plus an extension, X. And the other side length, it was A, but it's been extended by some amount Y. Okay, right, there we go. So that creates your proper triangle. And then think about balancing forces. Remember the object's in equilibrium. So, you know, vertical forces are balanced, horizontal forces are balanced. Or you could potentially make a force triangle. Remember, that's a possibility too. There are 3 forces on this object, going up to the right, up to the left, and down. Those will make a triangle because it's in equilibrium. So I like it. It's a bit of a geometry question. I would consider making sine theta and cos theta, find an expression for those first, and then see if you can relate them to each other through various equations. So get some maths down on your paper, give it a go. Good luck. Okay, and there is the working. Be interesting to know if you did it in a similar way. It looks quite short and sweet here, but obviously it hides the, you know, all the dead ends and other possible, you know, redundant equations you might have come up with. I won't talk through it or read it out, but have a look at it. Worst case scenario, if you weren't able to find it yourself, make sure you can follow through this working and that it makes sense. Cool, and that'll do.